Okay, so moving on into bonding. Now we're into section 11.2, which starts to try to explain why bonds form. So we're going to learn about stable electron configurations and the localized electron model of bonding. What does a noble gas electron configuration mean? So take a moment, think about it. What do all noble gases have in common? Aren't they all found at the right end of the period? What it means is that all their orbitals, but especially their outermost S and P orbitals, are completely filled. Okay? Now, stable electron configurations, like I said, the outermost S and P orbitals are completely filled. And if you have, for instance, a metal and a non-metal forming an ionic compound, their electron configurations after compound formation are going to look like a noble gas. So here's a picture comes straight from, section 12.2, and it's trying to show here's sodium becoming a sodium ion and losing an electron. If you take a look, what electron does it lose? It uses its 3s electron. This is a shorthand notation, electron notation for sodium, magnesium, aluminum, oxygen, and fluorine. And you can see when it loses one, it looks like neon. Magnesium, which has 2 in its S2, loses 2, looks like neon. Aluminum, which has 3, 2 in its S2, 1 in its 3p, boom, it also looks like neon. Nonmetals, on the other hand, are gaining electrons. So here it's the shorthand electron notation for oxygen and fluorine. You can see that it's 2p4 here, 2p5, gain 2 electrons. It goes to 2s2, 2p6, which looks again like neon. Helium with that addition is neon, and helium with this addition is neon. So after bond formation, they all look like they have an electron configuration of a noble gas. So the stable electron configuration is the one where the valence electrons, remember those are the S and P orbitals on the outermost surface, so they're the S and P orbitals from the period the element is found in, are completely filled. All atoms in a compound have stable electron configuration. It doesn't matter whether it's an ionic compound or a covalent compound. This happens during bonding, and the question is how? So if you look at water, this is a very poor drawing, but oxygen is attached to 2 hydrogens. Each hydrogen, after bonding, looks like a helium in its outermost electron configuration, so it looks like it's completely filled. And oxygen looks like neon, so I didn't show the 1s orbital for this one, but it's 1s2, 2s2, 2p6, which is the electron configuration of neon. So after bonding, both oxygen and hydrogen look like a noble gas. Now, this description of how bonds form is referred to as the localized electron model of bonding. Now, this applies to covalent compounds. In this model, it states that covalent bonds form when half-filled atomic orbitals of the 2 atoms overlap, and they will then form a new orbital that has 2 electrons. It's really called a molecular orbital, but whatever. Overlapping atomic orbitals works for this. So the electron configuration of oxygen, you can see, has 2 half-filled p suborbitals. And if you look at hydrogen, hydrogen's got 1 half-filled 1s orbital. So if we can overlap some of the 1s's with these half-filled 2p's, we can get a stable electron configuration that looks like neon for oxygen and a stable electron configuration that looks like helium for hydrogen. So here's a picture. So here's a hydrogen. It's only got a 1s orbital, so it's just a sphere. It's got 1 electron in it. Here's another one, 1 electron. Now we're only looking at the 2p suborbitals of oxygen. Remember, the 2s suborbital is already filled, so there's no half-filled orbital there. It itself is not involved in bonding. But the 2py is filled. It's got 1 spinning up, 1 spinning down. 2pz has 1 spinning up and a space, and 2px has 1 spinning up and a space. So our half-filled 1s orbitals of hydrogen are going to overlap our half-filled 2p suborbitals of oxygen. So we'll end up with our 2pz getting filled and our 2px getting filled. So the 2pz is here getting filled and the 2px is here. So you notice now I've paired the electrons. So in this overlapping space, they're now paired because there's 2 electrons there. They're paired here too. These are actually the same space. I just drew them, on opposite lobes. So we don't see that 2s2 orbital of oxygen. It's there, all right? Oxygen has the outermost 2s2, you don't see the 2s2 oxygen, yeah. The outermost layer is 2s2, 2p6 when it's bonded, and the outermost s and p orbitals are completely filled and it looks like neon. Okay, what about ionic compounds? Ionic compounds form when metals lose electrons and nonmetals gain electrons to attain this noble gas configuration. So electron configuration of sodium, you can see, has one electron in the 3s. Let's take a look at fluorine. Fluorine is, its 2p has one hole, okay, one space. So how do we form a chemical bond by getting a noble gas configuration? Well, what happens is sodium loses that one outermost electron. So its 3s orbital disappears. This is now a 2s and 2p, which you can't really see. I kind of am mixing ring diagrams and the orbital diagrams a little bit. So the fluorine will gain an electron to fill that final half-empty p orbital. So you see there's 2pz, it's only got one in it. The 2py has two, the 2px has two that are paired. The 2pz is now going to end up with two because one of the electrons is going to pop over from this 3s to go into the 2pz. The 3s disappears and now neon, it has like a neon arrangement for the sodium 1+ ion because now its outermost electron configuration is basically the same as neon. And as far as fluorine is concerned, since it gained an electron, now its outermost electron configuration also looks like neon. So you still end up with what looks like a noble gas, but instead of overlapping, you have electrons that actually are moving, causing the loss of an energy level on one and the filling of an energy level on the other. Both end up looking like a noble gas. Last thing to look at are ion size changes. Now, we didn't really talk very much. We didn't talk at all about this. I basically skipped it before, but I think this makes some sense. So for instance, if you have a lithium atom and it loses an electron, it gets smaller. Why? Well, think about it. There's still the same number of protons, right, with positive charge. There's fewer electrons. So those fewer electrons get pulled closer by the greater number of protons. So in all cases, when you lose electrons, metal ions get smaller. Now think about the opposite. When you've got nonmetals, they're, again, balanced with electrons and protons, but when they gain an electron, now there's an excess negative charge, and so the protons can't hold the electrons as closely, so the ions get bigger. So cations, metals, get smaller, anions, nonmetals, get larger.